Hey, everybody. And share screen. All right, so we're.
How's it going, Professor?
Oh, it's good. How are you?
Doing pretty good.
Nice, nice. All right, so we're going to finish up our SimVascular tutorial. So I did a little bit of experimenting over the weekend. So I found some easier ways to do some stuff. And so for I know some of you guys were having some issues with computer performance. I think a lot of that probably happened when we loaded the machine learning stuff. And so I found a way to do the segmentations, or more like I kind of remembered how I did these without having to do the machine learning stuff. So hopefully that'll be easier on your guys' RAM, and you can kind of it won't kind of crash your computer. So. And so if you can open up your project from last time, we'll start from there. Great. Yes. Yeah, all the lectures are recorded too. So, definitely use those guys. All right, so we'll start from here. So, if you have your path, then this is basically where we'll start. Okay? So everything up until path creation, all that was good. But then, once we go and make the segmentations, that's where we'll pick it up. Yeah, so if you want to open up your project from last week, you have to open up the actual project. So hopefully you've been clicking this button here for Save SV Project this whole time. And then what you're going to do is you're going to go File, Open SV Project, and then you're going to navigate to the folder where you save the project. Yeah. And so if you go, go to that folder, you should see a folder that looks like, or you should see, this kind of folder structure right here. So you should have images, meshes, models, paths, segmentation, simulations. And so once you get here, you just click select model, and then that will open up your project for you. Yeah. Nice. Great. All right. So if you're just joining us, we're gonna pick up from where we left off last week on the SimVascular tutorial. So if you can open up your project, that would be a good place to start. So I did some more kind of playing around with it over the weekend. So I found some better and more reliable ways to do it that hopefully won't crash your computer. Because I realized, last time when we tried to load the machine learning stuff, that was kind of a big burden on your RAM, and so I think it caused a lot of you guys to have issues with your computer. So there's a better way to do segmentations that we'll talk about today. But if you want to open up SimVascular and open up the project from last week, that's going to be our starting point. Okay. All right. About 20 more seconds, and then we'll get started today.
Sorry, Professor, you said in opening our file, go to Open SV file and then go to where?
Yeah, you want to go to Open SV Project and then go to the folder where you saved your project. So last week when you created your project and you were saving, it should have created kind of a folder in there for you. And so if you go to the File Explorer and you go to this location, actually, where is this code? Okay. Let's go CSUF. Well, this is my okay. All right, so this is the project that I made last time called Tutorial Project. And you can see in here, I have all these folders, and then there's an additional hidden file here called .svproj. And so if you go to that folder from within SimVascular and open it from there, that will open up your project.
Okay, thank you.
Mm-hmm. All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing?
Wait, how do I open my project again?
Yeah, so you're gonna go File, click Open SV Project, and then you're gonna navigate to the folder where you save your project. So when you create a SimVascular project, it creates like a whole folder for you, so it holds all of this information here. And so you're just gonna go to that folder and then click Select Folder, and that'll open up your project for you. Yeah.
Okay.
Mm-hmm. Okay, and so today what we're going to do is we're going to kind of pick up our tutorial. And so we didn't get a chance to quite finish it last time. And so I want to make sure that, we're all able to kind of do the paths and the segmentation and the modeling today. And I found some better ways to do segmentations that hopefully won't crash your computer. Because I know, when we tried to load the machine learning stuff last week, that placed a big burden on everyone's RAM. And so I found a better way to do it that didn't have to do the machine learning stuff, because the machine learning was kind of crappy right now to begin with anyway. So there's a better way that we can do the segmentation that will I think make segmentations that look better and also is easier on your computer. Okay. Right. So if you're opening up your project again, it should be the folder itself. It's not the file. Yeah. And so you have to open up that folder from within SimVascular itself. So you have to launch the SimVascular program first, and then click Open SV Project, and then go from there. Okay. All right. So our starting point today is actually going to be our path, and so hopefully you still have your path from last time, and so we're going to start from here. So I'm going to go over kind of one important thing for the path, and then we'll go and kind of redo our segmentation part with kind of an easier way to do it. And so before we get started, are there any questions? Okay. Oh, actually, there's a student came to me with a good point last week too. So, I know last time, a lot of you guys were having some rendering issues with your model kind of looking like zebra stripes. And so Isaac actually did some investigation for me, and he found that if you make it so that the SimVascular just uses your dedicated GPU to all the graphics processing, that kind of helps alleviate that. Because I think if you don't set that setting, then you might end up with some weird rendering stuff. And so if you change the settings, I think you have to do it from Windows. So I don't think you can do it, or maybe we're here. Properties. Anyway, I'll find the exact thing. So that was one thing I forgot to look into over the weekend. But I'll show you kind of where you can do that, and I'll send screenshots for you, through the Canvas site. Okay. And so actually, before we get started today, I do want to, let you guys know that, there are tutorials and there is documentation for SimVascular besides this class. Okay. And so, of course, we'll be doing things, through the lectures. And so you'll have my recorded videos. But if you wanted to have kind of a text version of the documentation, that exists for you. Okay. And so if you open up your web browser and you go to simvascular.org, okay, and you're going to end up on the same site through which you downloaded it. If you click this button up here for documentation, okay, it'll take you to all these user guides here, okay? And so everything that we're actually doing in the class, so all these tutorials are outlined here in this documentation, okay? And so, what we're doing right now is modeling. And so you can either click, the modeling guide here, or you can click the quick guide, okay? And that will show you kind of everything that you need to know. And so if you're kind of like me, so I'm kind of like an old school guy. So, for me, I prefer to have kind of, text representations of things just so I can kind of easily go back and refer to it. All of this is here for you. And so, if you don't want to, look through our lecture videos to find one specific thing, I think the text documentation is a really good resource too. Okay. It's not perfect, but it's, it at least shows you some things. So you can see here that they have some images here of path planning. And they're going to do segmentations and all that stuff as well. Okay. And so that's, I want to make sure that you guys are aware of that too, so that you can use that, as a resource for you guys. Okay. Okay. And so let's bring it back to SimVascular here. And this is, one of the main outputs that we made last week, which was the path. Okay. And so if you remember from last week, the point of the path here is to kind of trace out kind of the center line paths of all our vessels of interest. And so for this particular vessel, we started with the aorta, and then we follow the aorta down, to the bottom of the image data. Okay. All right. And
Wait, Dr. Tran, how do I get that image on my screen? Like right now, I'm looking like at the 4 different images.
Oh yeah. So the probably where you started was probably something like this, right?
Yeah.
And so to get in order to get just the path, you want to take the 3D view, which is in the bottom right, and then click this square right here in order to maximize this. Okay. And then to hide all of these image planes right here, you're going to click right here, where in the top right there's kind of a little crosshair, and then you want to uncheck the setting here for show crosshair, and so that will hide that, so that you're just looking at your path.
Okay. Thank you.
Mm-hmm. Okay. And so if you remember from last week, some of you guys had the issue where when you were creating your segmentations, some of them were kind of overlapping with each other, and that caused some errors, right? And so kind of the main culprit for that is if you have a path here that's kind of what I like to call kind of rough, okay? And so you can see here that what I have is a path where I've defined all of these path points, and it literally just drew a straight line in between each of those path points. And so what can happen sometimes is when you're kind of making a turn around kind of a vessel that makes a sharp turn, you might end up with kind of a path that makes the sharp turn, and it makes it so that your segmentations are kind of easily overlap. Okay? And so you usually want to avoid kind of rough looking or uneven paths like this. And so when you're in the pathing menu, so just make sure you can double click this path here on the left side, and you open up this menu right here. You'll notice that there's a button here for smooth. Okay. And so what this will do is this will automatically smooth your path. So it'll still follow the same trajectory, but it'll make it so that it's smooth, so that, you know, it'll be easier to put segmentations. Okay. So I'm gonna go ahead and click this, this button smooth right here. Okay. And then you'll see this new window here pop up first. It'll say smooth current path. Okay. And so usually for this, you can just take the default settings. Okay. And so for this, I'm just going to click OK. Right. And then what you'll see from there is that the path here is significantly smoother than what it was before. Right. So all kind of the uneven sections, all of the kind of the scraggly parts are all kind of smoothed over. And now we have this kind of nice smooth curve that we can work with. It'll be a lot easier to put segmentations on there. Okay.
Professor?
Yep.
How do you, so that right panel for me on SV path planning, it's all gray. How do I like activate that?
Yeah. So so if you're getting kind of a right panel that's all gray, you want to make sure that you've left click your path right here on from the SV data manager. And so the way SimVascular works is that it has kind of they call it like an active object. And so you want to make sure that your path is active in order to activate the right panel. Yeah.
All right. Thank you.
Mm-hmm. Yeah. And so, you know, smoothing your path is optional. So, you know, it's not something that you have to do, but it can help a lot, because when you're putting in segmentations, you know, you really want to have a smooth path so that it's a lot easier to kind of make those cross sections and make sure that they don't overlap. Okay. Okay. And so that's basically how you would smooth a path. And so, you know, if you have, you know, especially for your final projects, if you have vessels that kind of curve quite a bit, you know, and for those of you who are going to end up doing blood vessels in your brain, like the cerebral vasculature, then that's going to happen a lot there. So the smoothing function will probably help you guys out. Okay. And so our next task here is to, question. Do you stick with the default Fourier number? Yes. Yeah. So just the default settings are usually fine with that. Yeah. Mm-hmm. All right. And so the next thing we're going to do is we're going to make a segmentation group. So just like before, we're going to right click segmentations, and then we're going to click a create contour group. Okay. And so you can go ahead and give this a name. Right. And so, you know, usually you give your segmentations the same name as your path. So I'm going to call this our aorta segmentation group. Okay. Right. And if you recall from before, you know, this is the part where we have to trace out kind of the cross-sectional area for our blood vessel. Okay. And so this is the part where, you know, last time I think we did two methods. We tried machine learning and we tried spline poly, right? And so spline poly is still good. And so, you know, there might be some cases where you might have to draw things manually, but the machine learning didn't really work as well. And it seemed like it crashed half your computers too, just because it had to load everything onto memory. Okay. And so there's a better way to do this. And so the way that we're going to do this is with thresholding. Okay. And so the way thresholding works is that it basically looks at the medical image data and it finds areas where it's bright, and then it draws a contour basically around all the bright parts. Okay. And so basically it's looking for a threshold through which to cut off, you know, where it's not going to look anymore. Okay. And so using the thresholding is really simple. And so you're going to left click threshold here. Okay. And when you left click threshold once, you should see that this new menu appears here for all the thresholding settings. Okay. And so we're not going to change anything here. Right. And so after you click threshold, what you're going to do is you're going to mouse over to the left side of the screen where you see the vessel cross section, and you're going to click and hold, and then you're going to drag your mouse. Okay. Actually, click thresholding one more time. Okay. So actually, you want to make sure that threshold is highlighted blue in the menu right here. Okay. And so when threshold is highlighted blue, you're going to move your mouse over to the left side where you can see the vessel cross section, and then just click and drag. Okay. And then eventually what you'll see as you're clicking and dragging your mouse, that a vessel cross section is forming. Okay. And so you want to kind of stop this when it's kind of fitted around your vessel kind of well like that. Okay. Okay. Right. And so just to kind of go over that again. And so basically the way that we're producing segmentations is we're using this thresholding tool. Okay. And so you're going to click this thresholding button. And so you might have to click it twice until it's highlighted blue, which is kind of what I'm showing right here in the on the Zoom call. Okay, so you want to make sure thresholding is highlighted blue. Okay, And then you're going to, after this is highlighted blue, you're going to bring your mouse over to this top left view of the medical image. You're going to click in the middle of the vessel and then drag your mouse up and down until you get a contour that fits to your vessel pretty well, like this, okay? And so the red line should kind of hug around your vessel pretty well like that, okay? All right, and so what you should see is that this method here produces a much nicer looking cross-section without, you know, having to crash your RAM and stuff like that, right? All right, so is everyone able to use the thresholding tool in order to produce this the segmentation?
Wait, so you said to go to segmentations and create a new contour, right?
Yes.
And then you said to name it the same name?
Yeah, same name as your path. Yep.
It doesn't let me though. It says that I already have one.
Oh, so you if you already have one, then you can just name it something else. Yeah. So I started this project from before, so I basically deleted the group that I did before, and so you can either delete that old one or you can just give this one a new name. So either one's okay. Yeah.
Okay, thank you.
Okay. So was everyone able to use the thresholding tool to create this this contour group or this contour? Okay. All right. And so, you know, we're going to do one more thing here. So because, you know, the thresholding, even though it does a pretty good job here, the exterior, you can see it's a little bit scraggly. And so, you know, the reason for that is just doing a straight up threshold on your image data. So it's literally looking for all the pixels that have kind of the same image intensity as your blood vessel. Okay. And so, you know, when we produce a solid model for this, we want to kind of smooth this out. So just like before, we're going to click this button for smooth. Okay. Right, and so the smooth button is here on the right side of the screen, right? And then clicking that button will smooth your segmentation group, okay? And so what you see now is kind of a much smoother, you know, blood vessel cross section here, okay? Right, and so just like before, you know, you're going to go down the length of your vessel, and you're going to use basically the same methods to produce the cross sections, okay? And so you're going to start with thresholding, make sure that it's highlighted blue. Go ahead and left click on the image. Just go drag your mouse up and down until you get a contour that looks like that. Click the smooth button to make sure it's smooth, and then move on to the next cross section. Okay. Right. And so if you have thresholding down, go ahead and do this for the entire length of the vessel. Okay. And so basically until you reach the end of your path. All right, and then just like before, you know, if you want to just kind of follow along and kind of just watch me do this and then go back and do it later yourself, you know, that's perfectly fine too. Okay? So that's kind of the benefit of having these lectures recorded. And so I'm going to go a little bit fast because I didn't plan to spend today on this, but you know, definitely go back and watch the videos if you're having trouble with this. Right, so you can see with the thresholding tool here, we end up with, you know, a lot, you know, it's a lot easier to produce these segmentations, and they all look really good. Okay. Right, so as long as your segmentations are hugging your vessel kind of around the outside like that, then, you know, we're doing a good job here. Okay. Okay. All right, so that's the last one that I'll do. Okay. All right. Any questions on this? Yeah, this is much better than machine learning. Yeah. I don't know what happened with machine learning. So actually, you know, believe it or not, the machine learning was designed to do this faster than this. But for something happened with the machine learning where it's kind of sucky right now, and so we're kind of we're going to avoid it for now. Okay. And so from here, you can see that we've produced kind of the exterior for our blood vessel, but it looks a lot better than it did before. Right. Yeah. So right now I'm actually showing you a different method than what we did from last lecture. So last lecture we produced these segmentations, but we used different methods to do it. And so today I'm showing you the thresholding tool, which is kind of an easier way to produce these segmentations, which is different than the machine learning and different from the spline poly. Yeah. So it's just kind of a different way to do what we did in last lecture. Okay. Okay. And then now that we have our segmentation groups done, now we can go ahead and create our model just like we did before. Okay. So we can go ahead and click Create Solid Model. Okay. So just like we did before, we can go ahead and click Create Model. Okay. And that's going to loft all of our segmentations together. And now you can see we have a solid surface just like this. Okay. Right. And so there is our blood vessel. Okay. Or one of them at least. Okay. Okay. And so if you made sure your path went all the way to the bottom, you should have a blood vessel that kind of looks like this. Okay, actually, let me turn off this path. And so you should see the blood vessel come down. It should make a turn. There's kind of an expanded area right here, and then it kind of snakes around just like that. Okay. All right. And so I know kind of, just judging from everyone's screenshots last week, everyone was kind of at a different point with their paths. And so yours might not quite look like this. So yours probably might stop short, depending on where you stopped for your pathing. But if you made your path go all the way to the bottom of the image data, then this is kind of what you should see. So if you have this, great. But if not, don't stress out about it too much. Just kind of when you kind of work on this tutorial later, make sure that your path goes all the way to the bottom. Okay. And so if you see this, you can keep following along. But if you don't have something that looks like this, then don't worry about it too much, because the next part is pretty important, and you kind of need to have a longer blood vessel in order to do it. Okay. All right. So are there any questions on this so far? Okay. Okay. And so this next part, if you don't have a blood vessel that looks like this, I'm going to ask you to kind of stop what you're doing and just kind of watch, because this is probably the trickiest thing to modeling your doing this geometric modeling. Okay. Because what we're going to do next is we're going to make a vessel that branches off this guy. Okay. All right. So let me actually return to the 4 image datas. Okay. Let me turn on the crosshairs again right here. Okay. Okay. And so, if you kind of remember, we were working with this in this image plane right here. So we're working on the top left one. Okay. And then if you remember, when we got down, eventually the vessel kind of split in 2. Okay. So let me kind of get to that point right here. Okay. And so if you remember, there's a part eventually our main aorta here split into 2 vessels, and then what we did was we just followed one of the blood vessels down. Okay, and so that's what you kind of see here highlighted in white, which is the path that we've already taken. Okay, but most blood vessels and most of the projects that you're going to do is going to consist of more than one blood vessel, right? And so what we need to do at this point is we need to add another path in order to get that branching vessel. Okay. Right. But adding a branching vessel here is actually pretty difficult. And so it's, I'll show you kind of this case, which, this case, fortunately kind of works out pretty well. But, for your projects, it's going to be a little bit trickier than this. So I'm going to kind of, go a little bit slow here and explain every step, and just kind of make sure that you kind of do this kind of these steps too, right? And so there's a big section of this in the online documentation too. And so if you go to the online documentation, where is this? there's an image here for it, but they've kind of rearranged the documentation on me. So, but there's a big section on how to create a branching vessel, because basically what's going to happen is you're going to create a new path, a new segmentation group, but that new path, a new segmentation group has to fit within your existing vessel right now. Okay, because all we've done so far is we've just created one vessel, and that vessel, you can almost think of it as like our base vessel. Okay, and so all other vessels that branch off from this have to fit inside that base vessel. Right? And so just like before, we're going to start with a path. Okay, right, and so we're going to create a new path right here. So to create a new path, we're going to right-click Path and click Create Paths. Okay, and just like before, we're going to give a name for this path based on the blood vessel that it models. And so, you know, for this kind of model right here, you know, the other branching vessel that's going to come off is known as the iliac artery. Okay, and so I'll call it the iliac, just like that. Okay, and just like before, we're going to open up this menu right here, and then what we're going to do is we're going to place path points down on SimVascular in order to trace out that path. Okay. Okay. Right. And so the first tricky thing that you need to kind of ask yourself is, you know, where do we want to start this path, right? And so when you start a path for a branching vessel, it's very tempting to start from a place that looks like this on the top left, right? And so on the top left here, you kind of see the vessel is clearly bifurcated. And so we kind of have two splotches here. And so it's very tempting to make your first point in the path to be this point where it bifurcates, okay? And so I'm going to tell you that this is very tempting, but don't do it, okay? Because what you want to do is you want to make sure that this blood vessel, or this branching blood vessel, joins kind of very smoothly together with its parent artery, okay? And so in order to do that, we need to start its path a little bit farther up, okay? And so what you need to do is you need to change the image data here. And so in this case, I'm kind of scrolling up on the image data, okay? And so you can see I'm coming up slowly. And you want to get it to the point where both of those blood vessels look, you know, before they bifurcate, okay? All right, so let me go a little bit slowly again too, okay? So we're going to start here. And so we're going to start at a location where you can clearly see the vessels have bifurcated, and you want to move up to a location where they haven't bifurcated yet, okay? And so I'm slowly moving up on the image data where they're coming together, okay? And then once you're at this point, what you can do here is you can start your path here. Right, so let me zoom in a little bit, and let me add the first path point right here, okay? Right, and so what this will do is this will create your new path will basically start from a place where the two vessels are still merged, okay? So they haven't bifurcated yet. And this will allow you to basically make sure that your branching blood vessel will be joined perfectly with your main vessel, okay? Okay, and so from here, you can then progress downwards and then progress to a point where the two have separated. Okay. So let me put another path point here. Right, and so you can see now that they've already separated, but we already have two path points that are upstream of this, so we're good to go. Okay. Right, and so we can keep adding, you know, path points here. So let me change this to this view right here. Okay. Right. And so again, you know, I'm going to go a little bit fast just because, you know, I do want to get through some of the other lecture note stuff, but definitely, you know, refer back to this part later because it can be, you know, pretty tricky to do this part. Okay, maybe I'll do one more point here. Okay. Maybe one more. All right. Okay, so let me go ahead and clear this. Show this guy, right? And so these,
Professor,
yeah,
how would you know when to stop?
yeah. So
for
usually,
that one?
yeah. So usually you want to keep your path going until you don't see the vessel anymore. So usually you'll reach a point, and you'll either reach the end of the image data, which in this case you can go all the way to the end, or sometimes what will happen is that you'll kind of lose the vessel in the image data just because it kind of gets too tiny for the scan to pick up. And so you want to keep following your path until you reach that point when you can't see the vessel anymore. Yeah.
Okay. Thank you.
Mm-hmm. All right, and so it's kind of hard to see here because it's it's ginormous. Right, there we go. So let me change the size of these points. Okay. All right, so you can see right here we've created our branching path, and so this path comes off our main artery just like that. Okay. All right. And remember, the important part here is that we started this path from a point before the vessels bifurcated. Okay. Okay. And so from here, what you're going to do is you're going to create another segmentation group, right? And so, we're going to create a segmentation group for our second vessel here. So we need to make sure that we select the correct path for that. Okay. Right. And then just like we did before, we're going to create segmentations here. Right. All right. So at first it's going to be a little bit tricky because you're going to see, the blood vessel kind of look like this. Okay. Right. And so you might have to kind of travel down to a certain point where you can kind of see this blood vessel here. Right. And so this blood vessel here that you see that I'm circling with my mouse, this is our branching blood vessel that we're doing. Okay. Okay. So actually, let me take it up to a point kind of before it actually bifurcates here. Okay. All right. And so you're kind of seeing something that kind of looks like a hot dog right here, right? That's because we're basically viewing the blood vessel kind of spliced just like that. Okay. All right. And so what you want to do here is, if you kind of follow this down a little bit, you can start to see that the blood vessel kind of first starts to form right here. Okay. And so the way I like to do branching vessels is like this. So usually, I like to move this point here to a place where I can see the branching vessel very clearly. Okay. And so you can see here, I can see the branching vessel. I'll go ahead and create a segmentation here. Okay. And so same way I did before, so I'm going to use a thresholding. Okay. And then what I'm going to do at this point is I'm going to copy the segmentation. Okay. And so you can see here we have copy and paste. Okay. And that I'm going to paste the segmentation back up near the beginning of this blood vessel. Okay. And so you can almost think of this as kind of like a phantom segmentation here, because, the reason we do this is we need to make sure that our vessel actually starts back, in our parent vessel, right? And so in order to do that, we need to have a segmentation that's kind of all the way up at the top, right? Okay. Another thing that you see right here is that, this red circle right here, this is the segmentation that I just created. I want to make sure that this is kind of fully within this white outline here, which is the model that we have so far. Okay. And so what you can do is you can use the sliders here. So if you click, the middle of the segmentation, okay, and then you can drag the segmentation around like that, and you want to drag it so that it's kind of in the middle of your segmentation, your previous model like that. Okay. And if you need to make it smaller, you can do that by clicking this kind of thing at the end of the circle and making it a bit smaller like that. Okay. All right. And so what I've done basically is I've moved that first segmentation here to basically make sure that it's within our previous model, right? And because if you don't do this, what can happen is that you might have little segments of vessel that kind of poke out from your main blood vessel, just like that. Okay. And so you want to make sure that the first segmentation that you put is totally engulfed by your parent artery. Okay. And this is kind of one way to do it. Okay. And so once you have that, you can go ahead and continue placing segmentations down the length of your blood vessel. Okay. Right. So I have threshold selected. Okay. So let me go ahead and start doing segmentations here. Okay. Right. So I'll say it again to kind of emphasize it. So, when you're making branching blood vessels, you need to make sure that you do two things. So you need to make sure that your path starts from a location on your blood vessel where, before they bifurcate, okay? And so don't start your new path from a place where you've already seen it bifurcate, okay? Right, so that's one thing. And so the second thing that you have to keep in mind is that when you make your first segmentation, you have to make sure that that first segmentation is totally engulfed within within the parent artery. Okay. And so it's going to take some practice. So it's kind of one thing for me to kind of say it in words and to kind of, and to kind of show you here in SimVascular, but, it's a whole nother thing entirely when you go to do it yourself. So definitely, give this a try yourself. And it's going to take a few tries in order to get it right. Okay, let me just do one more. Okay. And so let me go ahead and turn off this path. Okay. And so what you can see here, I've created this branching blood vessel that comes off. Oh, actually, I have two that kind of overlap. Let's delete this guy. Okay. All right. And so let me go back to here. Okay. Turn off this crosshair. Okay. And you can see now I've created the segmentations for this branching blood vessel. All right. Okay. And so now let's add this to our model. And so, you can do this from the same model. You don't have to create a new one for this. Okay. And so what you can do is you can go ahead and click create model again up here. Okay. And then now that you've created a second segmentation group, you should see a second segmentation group appear from here. Okay. And so we're going to click this check mark here for use. Okay. We'll go ahead and click OK. Right. And then what you should see is now that you have a branching blood vessel. Okay. Okay. And so how do you know if you did this correctly, right? And so, one way to know if you did this correctly is to simply count the caps that you have in your model, okay? Right, because what you should see right here, after you created your model, is you should have a list of all of the faces in your model, okay? And if you click them, you can see that they actually highlight themselves, right? Right. And so what should happen is that, if you should count the number of caps that you have, and they should equal the amount of inlets and outlets that you have to your model, okay? And so in this case, we have 3 caps. So we have a cap here, that's where we started. We have an end cap where we ended our first vessel. And we also have an end cap for our second vessel that we just did right here, okay? And so we should have 3 caps that are in this list. And so if you count them here, you have 1, 2, and 3. So that's great. What can happen sometimes if you don't create this branching vessel properly is that you can have an extra cap, okay? And so what can happen if I didn't create this properly, you might see a second cap for cap iliac artery, okay? So it should say cap iliac artery 2. And so if you have more caps in this list right here than you do in your model, then probably what happened was that you need to work on your branching blood vessel here, okay? And don't be discouraged if that happens, because it happens to everyone, okay? Because a lot of times, it's hard to really get good at branching blood vessels without making kind of mistakes like this, okay? And so when you're trying this on your own, you'll probably reach a point where you'll have an extra cap here, but that's okay. If that happens, just kind of go back and kind of fix your model, just to kind of make sure that the branching blood vessel is totally engulfed, or the inlet or the beginning of that vessel is totally engulfed by the parent vessel. All right. So any questions on the process that I just outlined just now?
Professor, I have a question.
Sure.
If we do in the step of the models, can we change anything in the paths or segmentations?
Yeah. So if you've already created the model, you can go back and change those things. I would say that it's a lot easier to change your segmentations. And so if you want to make changes to your segmentations, you can do that. It's just that after you change those segmentations, you have to go ahead and refresh your model. And so after you change your segmentations, go ahead and click create model again, and then click OK. And then that will change your model for you. Yeah. But if you want to make changes to your path, probably what's likely going to happen is that you need to change your segmentations again after that. Okay. And so, just remember that everything kind of, proceeds kind of, linearly here. And so if you make a change to the path, then you have to make a change to the segmentation before you change the model. But you can go ahead and change anything here. You just have to kind of make sure that, you update kind of everything upstream of that, or downstream of that, before you get to the model part. Yeah.
Thank you.
Professor, why can't I create the model? Why is it like grayed out?
Yeah, so whenever you see things grayed out, you have to make sure that it's left, you have it selected here from the data manager. So you have to make sure that the your model here, the one that you want to create, is left clicked right here, and that should ungray out the create model button.
Okay.
And when we create the model, are we doing both the aorta and the iliac, or just
Yes.
The, okay.
Yeah. So make sure you have both of those checked. Right. Yeah. And then Ronald, to answer your question, actually right now you technically can't because turbulent flow requires some very specialized code to do that. And for SimVascular, it's actually just a very simple. I say simple, but it's CFD, so it's complicated. It just solves kind of just the base Navier-Stokes. And so if you want to solve for turbulent flow, you kind of have to add some terms to it, which SimVascular is not equipped to do. Yeah, but we'll talk about it. So generally, that might seem like a big weakness, but generally what we'll see is that the flow in the cardiovascular system is actually very laminar most of the time. Yeah, and so that's kind of why it was kind of decided to not add that in the code. Okay. All right. Any final questions on SimVascular? Okay. All right, so definitely, I know we went very quickly now, but definitely take the time and, definitely take the time and work through the tutorial yourself, because in the class, I have to go kind of fast just because it's, we only have a certain amount of time, but, typically when you do your tutorial here, sometimes it takes a couple hours just to do this tutorial yourself. So definitely, make sure you go through yourself and really kind of make sure that you nail down every step. Because in the lecture, it's kind of hard to kind of, make sure everyone's on the same page. Because a lot of times you want to kind of play with these tools and make sure they're okay. Yeah. And so just for reference, I make all of my grad students kind of go through this tutorial too. And I usually give them a week to kind of do exactly what we've done in the lecture here. So if it takes you, that long of a time to do this tutorial, don't feel ashamed. That's totally normal. And so I remember the first time when I did this tutorial, it took me about a week to kind of make sure I got a clean model from this. Yeah. Yeah. So what if I want to do a simulation for another planet like Mars? Yeah, then you would have to kind of go and modify the solver. So that's going to change things like the gravity and things like that. But SimVascular is kind of just optimized for just simulations on Earth. Yeah, but you'd have to change the source code for things like that. Yeah. So I know it's a little bit hard to keep up on, with the lecture, because, you're watching the Zoom and you're also doing this SimVascular at the same time. And so definitely, I would definitely recommend, going through this tutorial kind of on your own time, when you can kind of go slowly and kind of go through each of the steps. And then you'll have the recordings from the lecture to kind of act as a reference for you. Okay. And so now that we're done with that, and so you should be kind of equipped to to do the SimVascular, at least the geometric modeling part of this. Okay. And so what I'm going to do by the end of this week is I'm going to have a sign up sheet for your final projects. Okay. And so once I give you the final project and I give you the or once you pick a final project and I give you the image data for it, you can go ahead and start trying with the solid modeling for that. Okay. And it's going to be a long process. So definitely, it's a final project, but I'm giving it to you right now in week 6, because it's going to be, a pretty significant undertaking to build the model for this. Okay. And then, later on, we'll learn about how to actually run the simulation. Okay? But for now, just focus on the geometric modeling, and, and starting this weekend, you'll be able to start working on that. Yeah. It's like playing video games. Yeah, that's a optimistic, yeah, that's an optimistic outlook on that. But, whatever, whatever makes it go easy for you. Right. Yeah, so it's gonna be tough. Okay, so I'll tell you right now that this image data for the tutorial was a nice image data. So you can see the vessels very clearly here. So for a lot of your projects, your image data is not going to be as clear as this. So definitely kind of be prepared for that. So it's gonna be a long process. It's gonna be iterative, and don't be afraid to kind of reach out for help when you need it, because it's this is kind of the first time I'm doing this for a class this big. So, I expect there to be kind of a lot of bumps in the road. And so definitely kind of, definitely don't be afraid to reach out if you're having some issues on this. Okay? But hopefully, this will be kind of a tool, even though I know it's going to take a lot of time to learn, hopefully this will be kind of a really cool, tool, especially for a lot of you seniors that are graduating, hopefully a very nice piece to kind of remember your college days from. Okay, so with that, I'm going to go ahead and switch gears. And so I'm going to go switch back to my iPad here. And then I'm going to continue on with the lecture notes that we started last Tuesday, okay? And if you remember, what we were going over last Tuesday was the, general biomechanics for arterial blood flow, okay? And so this is lecture notes, let me see. This is lecture note 05 for arterial blood mechanics. Arterial biomechanics, sorry. Okay. Okay. And so it's been kind of a while since we went over this. So let's go ahead and refresh our memories. And so what we did last time is we talked about the waveforms that we usually see inside the cardiovascular system. Okay. Right. And so we had waveforms that kind of look like this. So let me draw the pressure waveform first. Okay. And so on the x-axis here, we have time. Okay. And on the y-axis here, we have pressure. Okay. And the normal units for pressure here is millimeters of mercury. Right. And then we said that the pressure waveform looks something like this. Right. Where we had kind of two phases here. So we had one phase where the pressure is generally going up, and this is cardiac systole. Right. Or in other words, this is the portion of the cardiac cycle where the heart is contracting. Okay. And then there's also the part of the heart cycle where the heart is relaxing, and we call this diastole. Okay. Okay. And so, that's the pressure waveform. And then we also had our flow waveform. Okay. It looks something like this. Okay. Where again, we have this section right here, which is systole. And we also have diastole. Okay. Okay. And so, I focus on the pressure and flow waveforms because these are, very important features of the cardiovascular system. Okay. And so when you go to the doctors or, when they're monitoring your health, these are some things that they want to, make sure that are good. Okay. Because it can say a lot about your health, where if they measure your pressure waveform and your flow waveform, and if they see some abnormalities in this waveform, like it doesn't have this kind of shape, then they can learn a lot about your system from there. And so a lot of times when you have disease, these waveforms will be affected. Okay. Okay. And so what we're going to do today is we're going to talk about how these waveforms actually come to be. So basically explain why these waveforms actually take these shapes. Okay. So any questions on this? Okay. All right. So let's talk about kind of this concept called the Windkessel model. And so the Windkessel model is actually kind of almost like a relic of the past, but basically this was kind of one of the first attempts to basically replicate the pressure and flow waveforms that you see in the cardiovascular system. Okay. All right. And so if you're wondering what the word Windkessel is from, Windkessel is a German word. Okay? And it's a German word for air chamber. Okay. And what it is that it kind of has three components to it, right? And so it has first of all, it has a pump, okay? And so the pump here is going to represent our heart. Okay. From here, it has what's called an elastic chamber. Okay. Okay. And then from there, it has a lot of very thin, thin channels. Okay. Okay. And what these thin channels represent is viscous resistance. Okay. And of course, this is kind of just a very vast simplification of this, because a real Windkessel model will have kind of more bells and whistles to it. But these are kind of the essential components that I want to focus on. Okay. Okay. And so this Windkessel model was kind of developed as a way to kind of replicate these waveforms. Okay. Because these waveforms here that you can measure, these are very kind of interesting things that you can kind of see. And replicating their behavior is actually more more complicated than it seems, because there's a few things here that we have to kind of highlight. Right? And so first of all, the first thing that we want to highlight is that in systole, right, what you see is that the pressure kind of increases rapidly. And so as the heart contracts, that's going to cause the pressure in your blood pressure to kind of raise up dramatically. Okay. Whereas in diastole, what you see here is that you have a decay in pressure, and so that the pressure will go back down, but it goes back down at a much slower rate than when it came up. Okay. Okay. Another thing that I want to highlight here is that this pressure, it never goes back down to zero. Okay. Okay. And so the minimum pressure that you experience here is actually greater than zero. Okay. Right. So all of these have a very important purpose. Okay. And so let's talk about the minimum pressure first. And so the reason we have a minimum pressure here that's not zero is because the cardiovascular system always has to be pushing blood throughout your body. Okay. And in particular, it has to push blood through your very tiny capillaries, because that's where all of the nutrients and oxygen and nutrient exchange is going to occur, right? And so in order to do this, there always has to be a non-zero pressure within your cardiovascular system. Okay, so you can't just your blood pressure never really goes down to atmospheric pressure, because there always has to be something to drive the flow forward. Okay, right? And the reason and the reason why we have this kind of different decay rates, okay, or the fact that our pressure increases much faster than it decreases, this has to do with the fact that our blood vessels are compliant structures, right? And so they're flexible. And so what that means is that when your heart contracts, your blood vessels are actually going to expand a little bit, because they're kind of almost like, you can almost think of them like a water balloon. Okay. And so when the blood vessels expand, what you can kind of think of it as there's blood that's being temporarily stored within your blood vessels, because the volume of your blood vessels is increasing because they're expanding. And then when the heart is relaxing, that expansion is kind of slowly coming back down, and that kind of releases its flow. Okay. And so that's the idea of this Windkessel chamber, okay, or this Windkessel model, right? And so what's going to happen first is that when the pump contracts, okay, when the pump contracts, it's going to drive blood, or it's going to drive fluid first into your elastic chamber, okay? And since this chamber is elastic right here, what's going to happen, the first thing, is that the elastic chamber will inflate, okay? Okay. And so from there, this elastic chamber is going to get bigger than it was before, right? So let me draw that. So this is kind of after the pump contracts, okay? And so now our elastic chamber is, it's a big chunker, so it's much bigger than it was before, okay? Because a lot of the flow that came out of the pump went into expanding the chamber. Okay. All right. And so now that the elastic chamber is kind of inflated as much as it can, when the pump is relaxing, okay? And so you can kind of think of the pump when it relaxes, it's almost not there. Then what's going to happen is that the elastic chamber is going to slowly deflate, okay? And then as the elastic chamber slowly deflates, it's going to push flow from the elastic chamber into the thin channels, okay? And so this kind of is a good model for how the pressure varies in the system, okay? Because when the pump first contracts, and the elastic chamber rapidly inflates, you're going to see an increase in pressure, okay? Then while the elastic chamber is deflating, right? So you can imagine the deflation is kind of a slow process because it kind of takes a while for the elastic chamber to squeeze blood through the thin channels, okay? And so as the elastic chamber is deflating, then the pressure is going to slowly decrease. Okay. Right. And all of that happens over one cycle, okay? And then once the elastic chamber deflates, okay, then the pump is kind of ready for its next charge, and then it's going to contract again. And so when it contracts, the elastic chamber is going to expand, and then it's going to deflate, and then expand, and then deflate, okay? And so, with this, scientists were able to kind of, experimentally replicate the pressure waveform that you see in the cardiovascular system, okay? And so relatively speaking, this is kind of simple because it's just a pump and a balloon and some thin channels. But people were able to use this to model the cardiovascular system. Okay, so this is kind of, you can almost think of this as kind of one of the very first models for it. Okay, and even though it's relatively simple, we can draw some very important conclusions from this that will help us inform some of our more sophisticated models. Okay. All right, any questions on the Windcastle model? Okay. All right, and so from the Windcastle model, we can kind of conclude that there are two kind of core features to arterial blood flow. All right, and these have to do with kind of our two end components for the Windcastle model. Okay? So we're going to ignore the pump because the pump is basically our heart. Okay, but we're more interested in how the blood flow occurs in our blood vessels. Okay? And so the first thing, our first core feature is the elastic chamber. Okay, and what the elastic chamber represents is the compliance or the flexibility of the large arteries. Okay. And so the large arteries in your cardiovascular system, those are flexible, and so they can kind of expand to store flow and then slowly contract in order to release it. Okay. And so this is a really important behavior because this is how we obtain that pressure waveform that I showed you kind of at the beginning of these lecture notes. Okay. And so, any kind of cardiovascular model has to be able to account for this effect of compliance or flexibility. Okay. And so the other core feature has to do with our resistance, or which is the thin channels which we had at the end of the experiment. Okay. And this is known as viscous resistance. Okay. And the viscous resistance here, this has to do with all the small capillaries or the small vessels. Okay. Okay. And so this is another important part, because one of the hardest things for your cardiovascular system to do is to squeeze your blood through all the really, really tiny capillary channels. Okay. So those capillaries are literally, the diameter of those capillaries are literally the diameter of a red blood cell. Okay. And so, this is another important thing that we need to model, because this is, one of the most important things that your cardiovascular system has to do. Okay. Right. And so remember, to overcome the viscous resistance, there always needs to be a mean pressure. Okay. And so even when the heart is relaxing, there still needs to be some kind of pressure that drives the flow forward through your capillaries, because your capillaries need to get a steady stream of flow in order for them to do their job. Okay. All right. Any questions on this? Okay. And so I want you guys to keep this in mind, because next week, what we're going to cover is a method called lump parameter modeling. Okay. And if you kind of remember that, when any kind of model for the cardiovascular system, right, or any kind of equations or any kind of modeling technique that we do, it has to capture these features. That's going to be kind of a good starting point for that lump parameter modeling. Okay. Okay. Right. So the Windkessel model, this was actually developed back in the 1800s, and so very, very early model. And even though it's fairly simple, it does do a good job of replicating those pressure waveforms, okay, which are really important. But the Windkessel model, in its simplicity, it kind of neglects one of the very important features of cardiovascular flow, which is wave propagation. Okay. Right. And so when I say wave propagation, what I mean is pressure wave propagation. Okay. And so the way to think about this is that, your heart, if you kind of feel your heartbeat right now, your heart is kind of always kind of contracting and relaxing, okay? And so every time it contracts, it contracts very quickly and very violently, right? Relatively speaking. And so basically every time it contracts, it creates, you can almost think of it like a pulse of pressure that travels along your blood vessel walls. Okay? Okay. And so this is separate from the blood flow. And so, the flow of blood, the fluid, is occurring within the interior of your blood vessels, right? But along the walls of your blood vessels, so along the solid parts, there's pressure pulses that are pulsing down, that traveling down there. Okay. And this is actually something that's actually really important for, how it forms, the pressure and blood flow waveforms, along the blood vessel tree. Okay. And so to kind of illustrate this, I'm going to draw an analogy. Okay. And so instead of a pressure pulse along a blood vessel wall, Now let's look at a string that we tie to a wall, okay? Right. And so if you can imagine, you tie a string to a wall, right? And so you grab the string with your hand, okay? And then what we're going to do is we're going to almost play jump ropes. We're going to basically put pulses down the edge of this, down the length of the string, okay? Right. And these pulses are basically going to be the same thing as our pressure pulses that happen in the cardiovascular system, okay? And so I'm going to use this analogy of a pressure pulse on a string to kind of illustrate, how that's going to affect, or what's happening in the cardiovascular system, okay? Okay, any questions on this? Okay. Okay, so let me draw our string again, okay? Okay. And so if you take this string and you kind of flick your wrist, you're going to have a little pulse that kind of appears on the string, okay? And then what's going to happen, intuitively you can kind of think about it, is that after you create the pulse is going to start traveling down the length of the string, right? And so after some time has passed, okay, usually not that much time, but after a little bit of time has passed, then you're going to end up with a situation that looks like this, okay? Right, and so the pulse is going to travel down the length to a different location on the string, okay? Until it reaches the wall, okay? Okay, and so the key thing here is that, once we create this pulse and it starts traveling down the string, it's for a lot of strings, it's going to go pretty fast, right? And so it's, it's not something that's going to go pretty slowly. But the important thing is that the travel speed for this wave is finite. Okay. Or in other words, what we can say is that we can observe this wave actually traveling down. So it's not like it travels very instantaneously, right? And so, if you play guitar, you're probably kind of familiar with this, with this phenomenon here, right? So if you strum a guitar string, you have the pulse will travel down the length of the string. So it's going to go really fast, but it's going to travel, okay? Right. And so eventually what's going to happen is that this pulse is going to hit the wall, okay? And then once it hits the wall, then the wave is going to reflect and come back the other way. And so once it hits the wall, then the following is going to occur, right? So you're going to have a pulse. And so let's say that after it reflects, it comes back on the same side, okay? Right? And then, the pulse is going to start traveling the other way, okay? Right. And so just to kind of summarize here, so right now we have a flexible string where we're creating pulses, right? And eventually that pulse is going to travel and reach the wall and it's going to reflect and come back, okay? Right. And so what we're going to talk about next is what's going to happen if we send another pulse down the string while we have this pulse that's coming back toward us, okay? All right, so are there any questions on this so far? Okay. All right, so let's see what happens when we send another pulse down the string. Okay. Okay. So let me draw one situation here. And so let's say that we've sent one pulse and it's already reflected, okay? And so this is coming this way. But then now we're going to send another pulse down the string again, and it's going to go that way, okay? And so eventually these two pulses are going to meet, okay? And when they meet, what's going to happen is that they're basically just going to add on top of each other. And so in a situation where both of the waves are kind of in the same direction, so let's say, they're both going up, these waves will amplify each other. Okay. And so eventually when they meet up, you're going to get something that looks like this. Okay. Right. And so you're going to get a big wave that happens right there. Okay. Just for a brief instant of time when the two waves coincide. Okay. And so after the waves kind of coincide, then they're basically kind of continue along with their along their merry way. Okay. Yes. So if you've learned this before, this is basically destructive and constructive wave propagation physics. Yeah. Yeah. And so this is the constructive wave propagation physics. So now let's go over the destructive one. Okay. And so let's say that we have our string. Okay, so this is versus something looks like this, right? And so just like before, we're going to have a wave that comes back this way. Okay. But now let's say that our second wave is going to be in the opposite direction. Okay. And so once this wave in the opposite direction comes and meets the reflected wave, they're gonna basically cancel each other out, or they're going to destruct. Okay. And so the net result of that is something that looks like this. Okay. Right. So if both of the waves are the same magnitude, then they're going to perfectly cancel. But a lot of times, after the wave reflects, it's going to be a little bit smaller than the incoming wave, which is a fresh one. And so you're going to have maybe something that looks like this. So just a little bit of a blip that goes down. Okay. Okay. Right. So this is a simple kind of example, and hopefully it's a memory refresher for what you've seen before. But this exact same thing happens in the cardiovascular system. Okay. And the main reason for that is because our blood vessels, our arteries here, are flexible structures. Okay. And so they might not be as flexible as a string, but basically if you pulse them, then what's going to happen is that there's these pressure pulses are going to travel down the length of your blood vessels. Okay.
On the first one, does the pulse stay does it not move, or does it move to the right or to the left?
Oh, do you mean the big one?
Yeah, the big red one.
Yeah. So the big red one, it's only going to be like that for just a brief second, because the waves are only going to interact with each other for when they overlap. But then after they're done overlapping, then the other two waves are going to continue along their way. And so after this, basically you're going to have a small red one that's going to, or actually the green one. The green one's going to show up on the right here, going this way, and the small red one is going to come on this way like that. And so this big red one is just kind of for that brief instant where they're kind of overlapping with each other. Yeah.
Okay, got you. Thank you.
Yep. Mm-hmm. Right. And so the same thing is going to happen in the cardiovascular system. So of course it's a lot more complex, because you don't just have a simple string. You actually have blood vessels that twist and turn and do all these kind of crazy stuff. But the exact same thing is kind of observed in practice. Okay? And this is actually a very a very key feature for cardiovascular blood flow. Okay. So any questions on this? Okay. All right. And so same thing happens in cardiovascular system. Okay. Except in the cardiovascular system, instead of a string, we have our flexible blood vessel walls. Okay. Okay. And instead of flicking our wrist, okay, instead of flicking our wrist to produce a wave, what you have instead is you have, your heart that's contracting. So every time your heart contracts, that creates a pressure pulse that travels down the length of your blood vessels. Okay. And instead of a wall, which is the place where the waves reflect, what you have instead are the capillaries. Okay. Because your capillaries, they're really tiny blood vessels, and because they're really tiny, they're also extremely stiff. Okay. And so because they're really stiff, they almost kind of act like a wall. So once a pressure pulse kind of hits the capillaries, because they're so stiff, the wave can't kind of progress past the capillaries. And so the waves kind of reflect and start coming back up through the arterial tree. Okay. And so constantly what you're having happening is what you have happening is you have forward going waves that come from the heart. Okay. So every time the heart contracts, it's going to send a forward going wave that goes forward. Okay. And at the same time, you have the reflected wave from the previous pulse that reflected off the capillaries and are coming back up the tree, okay? And then all along the cardiovascular system, you're gonna have these pressure pulses kind of interacting with each other, okay? All right. And so the speed at which the pressure waves propagate is called the wave propagation speed. Okay. Right. And this pressure wave propagation speed is actually it's different from the blood velocity. Okay. And so I think this is the part, and this is the part that confused me for the longest time too. Right. So whenever you have a blood vessel, okay. So let's say that we have a blood vessel that looks like this. Okay. Right. Inside the blood vessel, you obviously have blood that's kind of flowing here. Okay. And so the blood is traveling at a certain speed. Okay. And so right alongside that blood is you have pressure pulses that are traveling along, not inside the blood vessel, but inside the walls of the blood vessel, okay? Right? And so this speed right here through which, the pressure waves are propagating, this is the wave propagation speed, okay? And a lot of times, the wave propagation speed, or actually not a lot of the time, all the time, okay? Okay. A lot of times this is going to be much, much faster than the blood velocity. Okay. Okay. Right. So every time your heart contracts, it's sending these pressure pulses down the length of your of your blood vessel walls, and that's going much, much faster than your blood flow. Okay. And so if you want to put some numbers on this, then usually, depending on where you are in your body, the pressure wave propagation speed can be up to 5 to 10 times more, or 5 to 10 times faster than your blood velocity. Okay. And so, as you can start to see, we have a very, very complicated system because we have these pressure wave pulses, we have the blood flow, we have the pressure waveforms, we have, the compliance, and we have the resistance. So, it's a very complicated system. And so it's definitely right up there with, a lot of the more complex engineering system that you can think of. And so there's a lot of things to keep in mind, when we're modeling these things, and in our models, we want to hopefully capture as many of these properties as possible. Okay. All right. Any questions on this before we close up shop for today? Okay. All right, so that's all we got time for today. So thank you guys for tuning in. And so, definitely go and, do the SimVascular tutorial for yourself. And so I know in the lecture, there was enough time to kind of do everything because, you can see me doing it, but I've done this kind of dozens of times at this point. So definitely go and take the time, it's probably going to take you guys, some time to make sure to do the tutorial But make sure you go and do that because your projects are going to be a lot more difficult than that tutorial. All right. So thank you guys for tuning in today. You know, have a good rest of your evening, and I'll see you guys on Thursday. Thanks, guys.
Professor, I have a quick question.
Sure. What's up?
For 10, about, yeah, 10.
Mm-hmm. Yep, go ahead.
Okay, so basically for the homework, you know how you have that one equation that we wrote down?
Mm-hmm.
Is it always gonna be that particular equation, like using the same row of the spring stiffness matrix?
Yeah, so every spring and every truss will have that the same element stiffness matrix. And so how they're different is, you know, obviously the material properties like the spring constant, the Young's modulus, the area and the length, those are going to be different. But when you plug it into that stiffness matrix, those are always going to be the same.
Yeah, but like, for example, so finding the stress, right? You do E over L, and then you multiply that times from within the spring stiffness matrix, it's negative C, negative S, or the cosine, right? Negative cosine, negative sine, cosine, sine.
Yep.
And then you multiply that times the nodal displacements. Do
Yep.
you always use negative cosine, negative sine, cosine, and sine? Or
Yes.
does it differ?
No, for that one, you're always going to use the negative, you know, the negatives and the cosines and the sines, all of those should always be in the same place. Yeah.
Okay. All right. Thank you so much.
Yep. Mm-hmm.
Professor, can you hear me?
Yep. What's up?
So the blood vessels in our system, you said they act as the string, correct?
Yes. Mm-hmm.
And that's because they're flexible, but do they actually like move within our muscular system? Like, do they move actually?
Oh yeah, yeah. So you know, I'll probably have to show you guys some animations of this later on in the semester because doing a CFD with flexible walls is actually extremely complex. So it's, you know, we won't be able to do that in this class, or you might, you know, it depends on how quickly you move on your project. But there are simulations where you can actually see the blood vessels kind of expanding and contracting like this. So it's subtle. And so a lot of times you don't see, the deformation doesn't go beyond 10% of the vessel radius, but it does actually kind of move, you know, like this. And it's really cool to kind of see it very slowed down. And there's some medical imaging techniques where you can kind of see that really well too. So like if you have like an MRI scan that's basically taking place over 3D, and over time, you can actually see within the medical image data, you know, that expansion and contraction too. Yeah.
And the blood or the fluid does not move at the speed of the wave of the blood vessel.
Right. Yeah. So the blood is traveling at a different speed down the vessel because the blood velocity or the blood travel speed, that's more determined by Navier-Stokes more than anything. Yeah.
When you say the blood vessels, they move, are you just saying like they contract and they dilate?
Yeah. Yeah. There's some blood vessels that actually kind of translate, and like obviously, you know, you have blood vessels in your arm and you wave your arm like this, and you know those blood vessels will move around. And actually, you know, another blood vessel that moves around a lot are the blood vessels that are on your heart, right? Because if you imagine your heart is expanding, contracting, then the blood vessels that are on that are kind of moving like this as well. But most blood vessels, they're just kind of just a little bit, you know, dilate a little bit and then kind of come back, dilate and then come back.
So in that the Kessler, the example that you gave us, so the fluid within that model is at a certain rate, it's traveling at a certain velocity, and also the balloon is propagating the same way like the blood vessel here.
Yeah. So the Wynn-Kessel model, you're not going to observe the the wave propagation, just kind of just how it's designed, because it's literally just like a balloon. And so because the balloon kind of expands, kind of like this, it really kind of expands outwardly. You don't really see the pressure wave propagate because it kind of has to go kind of in a roundabout path. And so that's kind of an extreme example. And the Windkessel model, basically the point of that is basically all the stretchiness, and all the flexibility for all the blood vessels in your body, they basically put it into one place, into one balloon. But in reality, in your cardiovascular system, you have miles and miles of blood vessels, and they all can be flexible, right? And so what they attempted to do basically is to put all of that flexibility into just one place. And so when you kind of lump it together into kind of such a small area like that, you don't really get the wave propagation phenomenon, just because the wave will go past the balloon and then it's done. And so it kind of does like this. Because in reality, we talk about the waves traveling and reflecting, but since you have like literally miles and miles of blood vessels in your body, it's when a wave travels from your heart to the end, that's actually a long way for it to travel before it can reflect and come back.
I when you said that example about the this last page right here about the speed of the fluid and how the blood vessels propagate, it reminded me of that I don't know I don't know what they call it, but they have it like in dealerships about that. It's like an inflatable thing and like moves all around and they just
float. You mean the thing that goes like, yeah. It's kind of like that. Yeah, that's actually a good example because inside those things you have air that's kind of flowing through, right? So that's kind of like your fluid. But at the same time, you also the inflatable guy is actually kind of doing like this too, so you can actually see the blood, or not the pressure waves kind of propagate through that thing.
Yeah, so I was trying to think of that, like trying to visualize like what something I've seen that looks like that.
Yeah. No, that's a great example actually. Yeah, I think I'll bring that up next time. In that case, that case you actually kind of have the opposite, because the air is actually traveling through that thing a lot faster than the guy is kind of displacing like this. And the reason for that is because those things are made of a very thin fabric, which is really, really flexible. And so those things, you can twist it and kind of bend it without any trouble. Your blood vessels are a lot more stiff than that. So they're still flexible, your blood vessels, but they're still pretty stiff. And so what we'll talk about next time is that this wave propagation speed, it depends really heavily on how stiff your blood vessels are. And so the stiffer your blood vessels are, the faster the waves will propagate. And so for the car dealership guy, you kind of have the opposite situation. It's because that thing is so flexible that the pressure waves actually go pretty slowly through that thing compared to the airspeed.
Okay. Can you also say like it's like initially when you turn on a hose, like how it just like goes wild?
Yeah. No, it's exactly the same thing. Yeah.
Is what causes it to propagate is like you said the it's like the wave within the pulse. What did you call it again? The pulse of the wave?
Yeah, the pressure pulse. Yeah.
Pressure pulse. That's the pressure pulse. Okay. Wow. Okay. All right, Professor. I think that's enough for today.
All right. Yeah. No. Great questions. Yeah, I'll definitely bring up the example with the crazy guy for the for the next lecture. That's a good analogy.
Thanks, Professor. Have a good one.
All right. You too. Stephen, did you have any more questions?
I'm good. Thank you.
Okay. All right. So I'll see you on Thursday then.
See you.